In this tutorial, I am going to show you how you can compute FST values using VCFTOOLS. After that, we will visualize the FST values in a Manhattan plot using the R package called qqman. But before we start the exercise, let's look at what an FST value is. FST stands for Physician Index, and it is a population genetic statistic that is used to measure genetic differentiation between and within populations. FST values are usually between 0 and 1. A value of 0 indicates small genetic differentiation, and a value of 1 indicates high genetic differentiation. In order for you to follow this tutorial, you need to make sure your PC satisfies these requirements. You should have a Unix-like operating system, i.e. Linux or macOS. You should also have VCFTOOLS installed. In addition, you should have R and the R package called qqman installed. Instructions for installing these tools are in the description box. Now let's proceed. We are now going to download the example data. The data is available on one of my GitHub repos, which is here. I will leave the link to this repo in the description box. So we have the VCF file, which has variants for 60 Plasmodium falciparum isolates. Now the original data set can be found here on the malaria gen site. I will leave the link to this page also in the description box. So I took the original VCF file and then I downsampled it and also filtered so that I finally had high quality variants, and that is what I'm going to use. Okay, so the data here, I made mention it's made up of variant for 60 Plasmodium falciparum isolates. Okay, so these isolates were taken from 2 different countries. In other words, we have 2 populations here. Okay, so one population is from the Gambia and then the other one is from Bangladesh. So these are the 2 populations. Okay, so let's download the data. When you are here on the GitHub repo, you will see this file. So just click it and then you'll be sent to another page. So here, just click on the download button here. So click on the download and then you'll be asked to save it. Okay, that's what it is. But because I'll be using the terminal, I will download using my terminal. Okay, so I'll just copy the download link. So I'll right click and then I'll copy the link. And then I'll open my terminal and then download from there. Okay, I am in the terminal now. Okay, this is my command line. What I'll do first is to create a directory and then I'll seed into it. That will be my working directory. So I'll say make the, let's say FST. And then I'll cd into it. Perfect. So now I'm going to download the VCF file. Now with the download, you can use wget or you can use curl or you can use other command line downloaders, but I'll use wget or wget, okay, because I have that on my system. If you are using macOS, you can use curl also. So I will say wget and I'll supply it with the link to the file, the VCF file, which is here, and then I'll download it. Okay, so download has been done. Let's check the file. So if I do an ls, I'll find the file here. Okay, so this is the VCF file that I'm going to use. Perfect. Now we are going to explore this VCF file. Okay, so first of all, let's look at the samples. To get the samples, I say VCF query-l and then I'll supply it with a VCF file. So this will list all the samples. Okay, let me just repeat again. I'll say VCF query-l and then I supply it with a VCF file. And then I'll execute it. Okay, so I'll have all the samples displayed here. So you can also count them. If you want to count the same command, you use a pipe and you say wc-l. This will give you the number of samples. So we have 60 samples here. So the 60 samples that we have, 30 are from the Gambia, 30 are from Bangladesh. So let's look at it. And that is where naming convention also comes in handy, because if you have a good naming convention, then you can use some Linux commands to kind of get these populations, okay, into different files. But we will look at them. So first of all, let's just look at the samples again. I'll use this command this time. I'll do this. Yeah, so I want you to look at the sample names. So I have PR, and I also have PA. Okay, so some of the names begin with PR, some begin with PA. So the PR ones are those from Bangladesh, and then the PA are those from the Gambia. Okay, so if we are going to compute the FST values, then we need to have the sample names or the sample IDs, if you call it that way. We need to have them in different files. So the samples for isolates taken from the Gambia will have to be in one file, and then those taken from Bangladesh will also have to be in a different file. Okay, this should be text files. So we are going to use some Linux commands to get these sample names or sample IDs into their respective files. Okay, so I'll label them as pop1 and pop2 so that they match this VCF file. But you can use any name as well. It doesn't matter. But I just want to make sure I streamline things. Okay, so I'll start with PR first. So I'll say VCF query -L. I'll supply my file name. That's for the VCF file. And then I'll use a pipe, and I'll say grep, and I'll say PR like this. Okay, PR. Okay. So basically what I'm doing is that I'll have the lists displayed, and then the grep command here will look for this pattern PR. So all the samples that have PR in them, okay, will be displayed. So let's do this. Let's just look at how this can be done. So this is a sample command. So let's run this. Perfect. So you can see only the sample names beginning with PR have been displayed here. So that's it. But these were displayed. We want to save to an output file. So I'll also use this greater than symbol here, and I'll say pop1.txt. That's our population. Okay, that's the first one. Okay, so that's it. Yeah, so that's population 1. So if I do an ls, I'll see pop1. That is what I have here. I've used the cat command to display it. Okay, that's for pop1. Now let's do for pop2. So for pop2, that's population 2, will be VCF query -L. I still get my VCF file, and then I'll say grep, and this time I say PA. And now I'll just save it as pop2.txt. Okay, so that's for pop2. I'll use the head command to display, let's say, the first few lines here. Okay, so that's for PA. Okay, so now we have both files ready. Let's check them again. So let's do an ls here, and then you see these two files. So this is pop1, this is pop2. So now we have all the necessary files we need for computing the FST values. Okay, so let's proceed. So to compute the FST values, this is the command that we have to use. So let's do that. To compute the FST values, I'll say VCFTOOLS, and then I will specify the file type. Here we have a VCF file, which is gzipped. And so I'll say --gz VCF. And then I'll specify the VCF file, which is pop1 underscore pop2.vcf.gz. And then I'll give my FST command. So that is --weir -fst -pop. And then I'll supply the file name for population 1. So that is pop1.txt. And then I'll say --weir-fst pop. And then I'll supply pop2. And then I'll also give my output file. So that will be --out. And then I give the name that will be used. Okay, so this name will be the prefix for all files that will be generated. So I say pop1 versus pop2. That'll be the name. So I'll run this command. Perfect. So everything has been done now. So let's check the files. This was fast. Let's do an ls, and you see some file generated. So we have a log file here. We also have this one here. So this has the FST values. Okay. So let's do a head pop1 versus pop2 weir.fst. Okay, so we have everything here. So we have the chromosome number, we also have population, we also have the FST values here. Okay, now the FST, sometimes you have negative values, but these negative values, we always convert them to 0. Okay, because FST values, we normally put them in the range of 0 to 1. So if there is negative, we just make them 0. That's what you should know. Okay, so that's about it. So this file here, you can still view it on your PC. So let's check how to view that as well. So I'll just open it with any text editor or spreadsheet software, and then I can view this file here. So I'll try that now. Okay, so this is a file. Let me open it with a text editor. Yeah, that's it. Okay, so I have it here. You can also open it with a spreadsheet software. Okay, so I have it here as well. So you can open them and then inspect. Okay, so we have chromosome 1 up to chromosome 14. Okay, because that's for, we are dealing with Plasmodium falciparum isolates. So chromosome 1 to 14. And then we also have the position and then the FST values. So that's about it. So now we have our FST values. We can easily interpret and then explain the result if we visualize these values. So what we are going to do next is to generate Manhattan plots with the FST values using R. Okay, we are going to use an R package called qqman. So the scripts that I'm going to use, the R script that I'm going to use for the visualization has already been prepared, and it's also available on one of my GitHub repos. So we will download that first and then use it. So let's go to the GitHub repo, and then I'll show you that script. So this is the script. I'll leave the link to this repo in the description box. So just use that and then get the script. So this is the script. You can click it, and then when you are here, you can just read it, and you can also click on raw. If you want to download, just click on raw. And then here you can save it as a page. So you can save it. Just click on the save page as, and then it will be saved for you. So I will save it in my FST directory. Okay, so I will save it here in the same directory that my VCF file is, and then the FST values are. So that's about it. So I'll save it now. Okay, so I am going to take a look at that using my file manager. So here is the R scripts. So I'll just open it with R Studio. Okay, now I have my FST values. I also have my R scripts. The first thing I have to do is to load my library, which is qqman. This is what we are going to use to generate the Manhattan plots. I have tutorials that show how to install R package, so you can watch those videos if you are new to the R environment. Okay, so the links to those videos are in the description box. There's an online documentation that you can use to read more about the qqman package. So let's check that documentation now. So this is the R documentation page, and I will leave the link to this page in the description box. And so here we have the Manhattan plots function here. This page tells us the usage. So we have our Manhattan, that's what we call, and then we specify a data frame which has the values we want to use. We also have the chromosome, we have VPP, and then the others. I will explain this when we get to the R Studio. There is another page here that also has example commands you can use. So check this one also out. I'll leave the link to this page also in the description box. So the link to this page and this page, all of them are going to be in the description box. So use them and then get used to the qqman package. So let's get back to the R Studio. So I'll load my library first, and then I am going to set my working directory. The file that I'm going to use is in this directory, FST, and the absolute path is what I have given here. Yours is likely to be different, so make sure you put the appropriate path here. So I'll set this directory. I'm setting this directory so that when I'm reading the file, I don't specify everything again. And then if I'm also saving a file, then all the files that I save will be automatically stored in this directory. So it's always advisable to have a working directory so that you know where to find your files. Okay, so I'll set the directory now. And then I'm going to read the file that has the FST values. That is this one here. It's a tab separated file. And so that is why I have sep/c here. And there are headers. So I set that also to true. So I'll run this. And then I'll do a bit of exploration first. So I'll just say head FST just to look at some of the values. So we have here, let's also do a tail FST. Perfect. So I have that also done. Okay. Now we can check the number of variants or the number of SNPs here. So to do that, I can say dim FST. Okay, to get this here. Okay, so we have 2, 6, 8, 9, 4 rows and then 3 columns. So the rows here tells us the number of SNPs. Okay, it's always important to do some of this exploration. Now with qqman, if you are going to use it to generate Manhattan plots, it requires you to also have a SNP column. qqman was designed to visualize GWAS data. Okay, so to generate Manhattan plot using GWAS data. Okay, so we are using it for FST value, so we need to do some modification here. Now with qqman, I made mention that it requires you to have a SNP column. But if you look at our data, which is here, let's look at the columns here first. Let's say column names FST. We have 3 columns: Chrome, posts, and then the FST values. We need to add a SNP column. With variant, it's possible to perform annotation and get the names for the SNPs. That is something that I'll cover in another tutorial. But for this data, we don't have that information. So what I'll do is to create a dummy data. I'll create another column and then give some dummy names. And so the strategy I'm going to use is that we have 26,894 SNPs. So I'm going to label them using the numbers. So we'll have SNP 1, SNP 2, SNP 3 up to snip 26894, and that is what the code here will do for us. So first I get the length, that's the number of variants, and then after that I create a column, and then I add this name snip, and then I add the number, so from 1 up to 26894. That is what we are doing here. Okay, so let's run these codes. Perfect. So let's do a head just to see what we have now. So you can see the snip column here. You can also confirm using the column names, even though you can still see it here. I will just do it again. Column names FST. So now we have 1, 2, 3, 4. 4 columns. Okay, so we are ready to go. We are now going to generate the Manhattan plot. So we will start with this one here. So with the Manhattan plot, if you are going to generate, you need the information. It is here. We read a table here, which is FST. So that is what we have here. And then we also need to specify the column for chromosome, and then the BP, that's the position. And we also need the FST value themselves, which is specified using P. Okay, that is what we have here. So the P will be used for the column that has the FST values. We also need the snip column. That is what this here does for us. And log P is set to false. With the GenomWide data, we have log P, okay, sometimes being used. So your P values are transformed. So we take the log of the P. qqman can do that. But in this case, we are not using it for GenomWide data. We are using it to generate plots based on FST values. Okay, so we are not using P values here. And so I'll set this log P to false. That is why it's false here, so that we maintain the values that we are using. And then I have Y lab and then X lab. So Y lab for Y label, and then X lab for X label. Okay, that's the label for the X axis and then label for Y axis. So I'll do that, and then I'll run it. Okay, so we have the plots generated here. So that's our first plots. If you look at this Manhattan plots, there are two colors. We have black and we have gray. This is the default color that qqman uses if you don't specify any color. In our code here, we did not specify any color, and that is why this was given to us. If we want to change the colors, then we need to include the COL parameter, which is here. And then we specify our colors here. So we are going to run the qqman command again, and this time we'll specify our colors. So we do that now. Okay, we now have a new plot with our colors, black and red. Let's change the color. Yeah, let's change the colors to blue and orange. Okay, we have that also here. Nice. I'll go back to the black and then red. Okay. qqman also allows us to highlight or annotate snips that have a particular FST value. So you do that by using the annotate p val parameter here, and then you specify your value, the value that you want to use. Now we are using 0.2. So let's run this code and see what comes up. Nice. So you can see some text here. These are the snip names. Maybe you may not have noticed. Let's just run again. Let's do this first, and then let's run that code again. This one, the one to annotate the snips. Perfect. So you can see them here. Now let's try with a different threshold. Let's use 0.7. I'll do that here. you can see that I added this thing here. Okay, this one by default is set to true. Okay, it's set to true. So even if I don't specify it here, like this side here, I didn't specify it, it's still true. And so it's the same output that will be given. So I just wanted to include it so that you know that there is an argument you can specify here in this function. So I'll run this, and now we have our SNPs here being displayed or highlighted. Now with qqman, the default behavior is to annotate the top SNP per chromosome that exceeds the threshold that we have set. So in this case, our threshold is 0.7. Okay, yeah, this one here is 0.7. And so probably you may think that because it's 0.7, we should have all the SNPs here being highlighted. But the default behavior is that only the top SNP per chromosome that exceeds the threshold will be specified. But you can change that behavior. If you want all the SNPs to be highlighted, then you have to specify false, okay, for the annotate top. So to do that, we run this code. This time we will set it to false, like this one here, F. We set it to F, which means false. So let's run this. Perfect. So now you can see all the SNPs, okay, that are above the threshold that we set. So we have everything here being highlighted. So that is how it is. So you can use this if you have some SNPs of interest, or in this case, if you want to look at SNPs with particular values, then this is one way to highlight them on your plots. Now let's proceed. Now with qqman, it also allows you to draw a genome-wide line. So genome-wide line in this context allows us to draw a line so that we can have our high FST values at the top and then our low FST values at the bottom. That is what this genome-wide line can help us to do. There's another line here called suggestive line, okay, that you can also use. But for this tutorial, we are only going to use the genome-wide line parameter here. So if you want to draw that line, then we use this to do that. Okay, so that's what we are going to do next. I repeat, if you want to include the genome-wide line, then you have to set the threshold, okay, using this genome-wide line parameter here. So you will set it to 0.5. That's what we have here. And then we also have this one here, suggestive line, which also allows you to draw some lines, but we are setting it to false. I decided to just bring this one so that you know that you can also draw another line using this parameter here. But for this tutorial, we are focusing on just the genome-wide line here. Okay, so let's say you want to draw a line on the 0.5 mark, then you set it here like what I've done here, and then you will run your code. So let's run this code. Perfect. So now you can see that a line has been drawn. That's what we have here. Now the SNPs that were highlighted are gone because we didn't include that here. And so you can do that. Let's do an interesting combination here. So let's just run this. Let's copy it again. We are going to run this same code to get this plot, but this time we also want to highlight the SNPs. So I'll add this too. So we are building upon what we've learned. So I will do this, and then you will see it's nicely done here for us. Okay, we can change the color of the Manhattan plot so that this red line stands out. So I can do that here. Let's say blue and orange. Let's do this and then see what comes up next. Perfect. So now we can see our genomewide line. We can also see this. So you can change this also. I mean, it all depends on you. So you decide how you want things to be, and then you use the appropriate commands to help you do that. So that's about it. I'll go back to this one and then get my genomewide line. Okay, nice. Aside the use of thresholds, you can also specify the names of the SNPs, and then qqman can highlight only those SNPs. So that will be the SNPs of interest. So in this case, I have given some example here. I have SNPs of interest, 3 of them, 1, 2, 3. And so you can feed qqman with this lists, and then qqman will just highlight those ones. So here I have my list defined here. And so what I do is to just come to the highlights parameter here, and then I will say equals SNPs of interest, which I have already defined here. So I'll run this. And so first I'll run this code so that the list is created. And then I'll run this code here. Perfect. That has been done. So you'll notice some points here, some green points here. These are the SNPs of interest. So we have them here. This. Okay. So let's just remove this color so that the green ones also stand out. So I will just run the codes here again, but this time I'll remove this one here. I want to use the default colors, and then I'll run it. Perfect. So now we can see our green colors here. So this is how we also highlight SNPs of interest. Let's say you have SNPs that are of interest to you. Then using the highlights parameter here, you can highlight those SNPs. Probably you want to do a presentation, or you want to generate a report and then talk about these SNPs, these 3 SNPs, or any SNP of interest. Then once you do this, you have only those ones highlighted, and it becomes easy for viewers to also see them and then appreciate what you have done. So that's about it. Before we end this tutorial, I would like us to check the FST values again. Let's look at the first 6 rows. And you will notice that some of the values are negative, like these ones here, the first 3, and then this one here. Okay, if the FST value is negative, that means that the FST value is very small, and that is why it's negative. Okay, so in case you use the values here, okay, to plot, and then you have some issues because of the negative values, you can change the negative values into 0 and then use them. Okay, so that's how you can resolve that issue, because FST values I made mention, they are typically in the range of 0 to 1. So maybe some programs due to the negative values may give you error, or maybe some of the programs may skip the negative values as well. So it's up to you to check to make sure that the plots that you are generating are what you are expecting, or what you expect. So I just do that. With this tutorial, I did not change the negative values to 0. I used all the values here, okay, because I realized qqman has a way to deal with the negative values. Okay, but we can still try, so that I'll show you how to change negative values to 0. Okay, and we also use that to test. I did a test earlier on, and I realized that the plot that I generated using these values were not different from the ones I generated after converting, or after changing the negative values here to 0. So let's just test. So what I'm going to do now is that I'll change all the negative values here to 0 with a single line of code. So I'll say FST dollar. Let me just do it here. FST dollar. There's a column. There's a column that has the FST values. And then I'll give my square brackets and give the same expression here, FST dollar WIR underscore qqman FST. And I'll say less than 0. So here I am looking at this column, and then I want to get all values that are less than 0. And then I'll say equals to 0. That means all values less than 0 should be changed to 0. That's what's here. So let's run this command. So now if I do a head, let's say head FST, you'll see that the values have been changed. Those with negative values have been changed. But I'll advise you that you always make a copy of the original table and then make your modification on it, especially if you're a beginner, so that you don't mess up your codes. Okay, so let's proceed. So now I have all the negative values changed to 0. So I'll generate the Manhattan plot again. So I will say I'll use this command here. I'll use the default colors. Okay, and then I'll run it. So let me run this, and then take note of this plot here first. So I'll run it now. Perfect. So you will see that there is no change here. Okay, after we have used the new table, which is here, the modified table. Okay, so this is what led me to believe that qqman has a way to deal with the negative values, and probably changes all the negative values to 0 and then generates the plot. So that's about it. So that's how we do it. So that's all I have for you for today with respect to visualizing FST values. Okay, and so with Manhattan plot, you can also use that to visualize TAGMSD. TAGMSD is another population genetics test statistic, and I will make a tutorial on that as well. So make sure you come back to this channel and then watch that. So that'll be all for this tutorial. Thanks for watching, and I'll see you in the next session. Goodbye.